Morning, everyone, and a few additional sugar kick from the fine donuts back there, and as we seatbelts here. First off, I'd like to acknowledge my co-authors on this work. Jared Grider, former student of KGS, has graduated and now has his degree in geology. Ethan Davis is a student currently working with UT. I acknowledge contributions from Bart Davidson and June Feng Zhu and Chuck Taylor. I put them as contributors just in case they want to disavow themselves from anything that I might say in this talk. So, as Jerry mentioned, energy issues are front and center in the state, in the Devonian Berea Sandstone play in northeast Kentucky, which has been very active for the last 4 or 5 years. We actually have horizontal fracking and horizontal wells occurring for the first time in the state. Historically, we've had fracking, but primarily in vertical wells. But this represents the first large-scale program in which we see fracking in horizontal wells. And in this particular play, we're in excess of 50 wells so far, and concentrated, as you can see, in this 5-county area of Elliott, Carter, Greenup, Lawrence, and Boyd. The fracking is actually occurring at relatively shallow depth, in many cases less than 2,000 feet, which is very different than what we observe in other unconventional resource plays in North America. So because of that relatively shallow depth, of course, the issue comes up is what effect, if any, does this have on potable groundwater quality and resources in the area? And the bottom line is that we probably are not in a very good position to answer that question because we really don't have a reference set of background data in which to reference to understand what changes, if any, of those have occurred. And part of that question, of course, is if you want to understand how fracking affects groundwater, if it does at all, and again, I want to emphasize if it does at all, you actually need to know the distribution of groundwater in the subsurface, correct? And so that's really the focus of today's talk, is what we know about the distribution of fresh water in the subsurface. I will add, as a final point on the slide, is that the volume of fluid that's being used in the Berea play is relatively small volumes, and it's on the order of tens of thousands of barrels, which is in contrast to things like the Marcellus and Bakken, which are 1 to 2 orders of magnitude greater in terms of volumes of fluid being used for fracking. So really the linchpin for the oil and gas industry in protecting groundwater is the surface casing. So when oil and gas operators drill wells, they install a series of casing in the well that include a conductor casing at the surface, a surface casing which is actually for protecting the groundwater, an intermediate casing which is intended to block off oil and gas flow from going into feed formations deeper in the hole, but also to keep the hole from sloughing. And then finally a production casing through which we actually produce, or through which the oil and gas is produced. Now, what we're really interested in is the depth of the surface casing, which is intended to protect the groundwater. That depth is often based on experience in the area, recommendations from the Division of Oil and Gas, and one of the important guiding documents in those depths is a map that was constructed in 1966 by H.T. Hopkins. So, as I'm involved in the Berea play, several operators asked me, well, what do we know about how deep we should be setting surface casing, given the shallow depths at which fracking is occurring? So here's the, so I went to the Hopkins map, and here is the map. I appreciate that you can't read the contours on here, but what Hopkins did was, he went through and defined areas where water had values of less than 1,000 parts per million. He called that fresh water. Anything greater than 1,000 parts per million fell into the category of salt water. He then mapped that so-called interface between less than 1,000 and greater 1,000 ppm water. And he did this using primarily domestic wells. So this is just a quick example. If you look at a close-up of one of those well entries on the Hopkins map, you'll see he documented total dissolved solids, chloride, the depth of the well below land surface, and then the depth of the well reference to sea level. So here's the first critical point that you need to tuck away in your cap as we go forward, is that he assumed that the altitude of the bottom of the well, reference to sea level, equaled the base of the fresh water. And as we'll find out, that's a grossly oversimplification of reality in the subsurface. So if we look a little closer into this northeast Kentucky County area, I just want to give you a sense for the humidity density and the variation that we see in that surface map by Hopkins. So again, northeast Kentucky, Boyd, Lawrence, Elliott, Carter, Greenup, kind of the epicenter of the Brea play. His map is based on 28 wells. So not a large number of wells spread through a large area. Accordingly, there's a lot of interpolation that happens there. But the other thing that Mr. Hopkins did is he also considered the influence of topography on the depth of fresh water, which is important to do. So in the general area, what he found is that that surface between the fresh and the saline water varied from 820 to 433 feet above sea level. So it's instructive at this point to actually look at a schematic of what the distribution of salt and fresh water look like on the surface, to understand some definitions, but also to understand the limitations of Hopkins' construct of this fresh saline water interface. So what we see in this little schematic diagram, you have a series of freshwater aquifers, okay? And there are 2 points that I'd really like to underscore here first, is that first off, topography does influence the depth at which we see fresh water distributed in the subsurface. And then the second thing, of course, is that a lot of these aquifers pinch out, so that you may have multiple aquifers on top of each other, and because of facies changes, they may not continue in a lateral sense in some monotonic fashion. So basically, no surprises here for us other geologists. These are fairly complex systems. And then finally, we get down far enough, we get into true saline water greater than 1,000 TES, right? So if we go back to the Hopkins definition, what he did is if we took 2 hypothetical wells, 1 and 2, what he said is that the base of the fresh water then would equal the TD of that well. In this case, the surface elevation shown with the black arrow minus the TD of the well reference to the surface shown with the yellow arrow. That then gives you the elevation of that so-called fresh saline water interface above sea level. So clearly, as we look at this, you can say, wow, that's quite an underestimation, right? The true depth of which we see the fresh saline water interface. So if you're using this as a guide then to make seeding judgments about surface casing, you could very well underestimate the depth at which you need to set the surface casing. So the important point here, point number 2 to tuck away in your cap as we're going forward, is that the Hopkins map likely underestimates the depth of the true fresh saline water interface. So when I looked at this map, I actually was a little bit appalled because I didn't understand that working within the time framework at that time, there are limitations. But what I picked up on in conversations with people is that this map was taken literally, which to me, I guess, was the cautionary note here. Maps are strictly interpretations, and we shouldn't forget that. So I asked myself, can we improve upon the Hopkins interpretation? So this map was constructed in 1966, and I said, we should have a considerably larger set of data in which we can add to the Hopkins map, potentially push this interface down, right, or at least give us a reinterpretation. So the reason is that with 40 or so years of development in the state, we actually may see deeper groundwater wells. So these dark blue wells would represent hypothetical wells drilled since 1966. So what happens now is that we now might be in a position to push down the so-called fresh saline water interface to a deeper level. Well, that's fine and good, but guess what? We're still above the true fresh saline water interface, right? Basically, we're improving the accuracy, but there's still some error in this effort. So just to look at this, what the effect of this effort, this is that 5-county area in northern Kentucky. Hopkins had originally 28 wells, and what we did is we queried the Kentucky Groundwater Data Repository to look for wells in which chloride values were below 500 milligrams per liter, and wells that were completed as domestic wells. That's actually a critical point here, is that we reason that if someone has a domestic well, presumably it's fresh water, even if we don't have chemistry data. So what happens then is we increase the number of wells now from up to 120 wells. So basically, the robustness of the data set increased by a factor of about 4 times. So now if we look at this, taking that data, we then initially machine contoured the data for the area using a program called Petro. Petro uses a totally statistical and mechanical process for contouring the data points. And, you know, I looked at it and I thought, well, that's fine and good, but, you know, I kind of have this retro streak in me and I couldn't avoid putting my pencil on the paper to do some contouring, right? So, if anyone, younger ones in the crowd don't know what that is, just talk to me afterwards. So anyway, yeah, so, but joking aside, the point is that machine contouring is not in a position to take into things like the topography influence on that interface, right? And I wanted to be sure that that was included in the interpretation. So what you see here, and these are 50-foot contours, this is that quote-unquote fresh saline water interface now recontoured in that area. And the important point here is not so much the values, is that, look at now what I call it. I can now call it the deepest observed freshwater. So what I'm trying to do is acknowledge the fact that there's some potential error in this, and basically get away from this notion that there's some absolute surface there that represents the fresh saline water interface. What we see here now, just to compare to Hopkins, is that we now see about 600 feet of relief on this surface. Hopkins map about 400 feet of relief on that surface. So we've increased that relief by about 200 feet. So there has been some measurable effect. Now, if we get back actually to the crux of the matter, is what effect does this have on the quality of groundwater, right? And so one of the important points, or one of the things that affects the potential of an oil and gas well to affect groundwater is what is the thickness of the interval straight up between the top of your well reservoir and then the base of your potable groundwater, right? So this is the same map we just looked at, but now what I've posted in red are the thicknesses from the top of the Devonian Berea sandstone well reservoir to the base of the so-called deepest observed freshwater. In other words, the confining interval thickness. And what we observe here is that that thickness of strata ranges from about 1,650 feet down here into the southeast part of the study area to less than 350 feet up in Greenough County. So definitely getting thinner up in this area. The other point I want to make to you is because that so-called deepest observed freshwater really does not extend down to the fresh setting water interface, what's the corollary for this map? The corollary is that we're actually overestimating the thicknesses of the confining layer on this map. So that's a good point to keep in mind, is the interpretation sometimes can carry through to the derivative products if you're going through an analysis process. So I was aware all along, being in the energy section, that oil and gas operators routinely documented the occurrences of fresh and salt water when they drilled wells, right? And the question was, and I recognized that, and it wasn't really that I thought that this might be a viable data source until we started going down this path of trying to map the so-called freshwater saline water interface, or the deepest observed freshwater. So I asked myself, could we actually pull out this oil and gas data where they record the intervals of fresh and saline water and actually produce a map that's less wrong, okay? So-called path to less wrongness. Well, and now it's shown schematically the oil and gas wells in green, right? And as you can see, they actually go through all the freshwater layers and into the saline water. And they started recording these operations around the mid-1970s. The question becomes, of course, is how good are the observations? So this is just an example of a driller's report from Lawrence County taken off the KDS website. And there's a variety of data reported here, but really what is of interest for today's talk is where they encountered the fresh water, okay, or the saline water. So this is just a standard view of that part of the report. And I actually sent out some emails to colleagues and I asked them, so well, how do you determine where water's fresh and where it's saline, right? And so here's the answers. Some, very few, actually will have, the driller may have a conductivity meter on location and measure the conductivity, so the gold standard, right? Some actually use salinity strips, but by and large, the majority of operators, they're on location, guess what? Right? So it's a taste test, right? And unfortunately, that's the majority of our measurements probably. So I haven't tried to determine, there's no way to determine that. It's likely that's the majority of our measurements. So now we go into this and we ask ourselves, okay, we have some subjective data. We actually use subjective data to decrease the wrongness that we have in the map. Sounds like a fool's errand to me. So I thought, well, let's go down this path. I got a summer student. Summer students are cheap, and let's see what we can do with it. So what I did is we went into Lawrence County and we pulled the oil and gas records for every other 1 minute Carter section within each of the 5 minute Carter sections in Lawrence County. Okay, so and then what we did is along north-south roads, we summarized the depths at which fresh and salt water were recorded in Lawrence County. So so what happens here over the next few plots, we'll actually see the summary. So if we go from west to east, we'll see the series of 79 5-minute Carter columns, the 80-minute Carter columns, 81, 82, and so on and so forth. So this is a plot, elevation of the well along the x-axis, and along the y-axis is the so-called deepest observed freshwater that's recorded in oil and gas records. Now remember back to that little schematic I showed you, is that topography has a first-order influence on the depth at which we see freshwater, correct? Well, what we see here now is that with increasing elevation, that there is actually a trend with the depth that we observe, deepest observed freshwater. And so that's the first observation that I see here. But the second observation is that we actually see maybe two trends here. The other thing I'd point out to you is that this is an edited set, and there were data that plotted elsewhere, and we were actually able to determine that probably the operator was just copying notes from one record to the other because you had multiple recordings of fresh water at the same depth among, a dozen or so wells. So we discounted those. So again, so I call this, does this pass the taste test? So indeed, it does look like using the taste test, operators were doing a pretty reasonable job at documenting the depths at which we see fresh water. So I want to wrap this up, and let's see what this looks like in the Lawrence County area. So again, along the x-axis is that series of 5-minute Carter columns going from 77 all the way to 85, and then the deepest observed fresh water. Okay, so there's a fair amount going on here, but let's step through it. So the averages based on the oil and gas data are shown with the red squares, and then the rectangles around them are the standard deviations. So basically a lot of variation in the data, and there's no surprise there, okay? We also recorded the maximum depth at which fresh water is recorded using the oil and gas records, and that's shown with the blue dashed line, okay? So if we just used the data from the groundwater data repository, that interface would follow the green circles here, okay? So quite a bit, the oil and gas data record the potential fresh water quite a bit deeper if we just, as compared to using the groundwater database. Similarly, if we just went by the Hopkins map, this is where Hopkins map the so-called fresh saline water interface, the profile through Lawrence County. So what we see here is a variation on the order of 200 plus feet deeper for potential fresh water in the Lawrence County area, just by going to the oil and gas, using the oil and gas data. So to wrap up, basically, just by selecting the groundwater database, we actually increased the robustness of the map, right? But even with that increased robustness, we were still probably underestimating this so-called saline freshwater interface. As I mentioned, the interval thickness, the confining layer, is accordingly overestimated. It does look like the oil and gas records provide an opportunity to improve the accuracy or the less wrongness of this map, if you will. And then last off, I'd like to say that Bart Davidson and Jun Feng Zhu are extending this effort throughout the state. And actually, one of our challenges going forward is how do you merge areas in which you have a lot of oil and gas data and those observations? How do you merge that in data in areas where you don't have a lot of oil and gas observations and you have to solely on the groundwater data? So that's our challenge going forward. Thanks, and I'm happy to answer any questions.